Epoxides, also known as oxiranes, are three-membered ring structures in which one of the vertices is an oxygen and the other two are carbons. As you can see in the diagram below, you have your oxygen attached to two carbons in a triangular structure.
Epoxides, although strained, are commonly found in nature. Here are two examples of commonly found epoxides in nature.
Ethylene oxide is the most important and simplest epoxide. It is prepared on an industrial scale by catalytic oxidation of ethylene by air. As you can see pictured below is a chemical reaction of ethylene oxide as the product.
Ethylene oxide is used as an important chemical feedstock in the manufacturing of ethylene glycol, which is then used as antifreeze, liquid coolant, and solvent.
Oxycyclopropane synthesis by peroxycarboxylic acid requires an alkene and a peroxycarbolic acid, as well as an appropriate solvent.
Commonly used peroxy acids include MCPBA and peroxyacetic acid. As you can see in the reaction in the picture, we will be using MCPBA as the peroxy acid.
The reaction is initiated by the electrophilic oxygen atom reacting with the nucleophilic carbon-carbon double bond. The mechanism involves a concerted reaction with a four-part circular transition state. The result is that the originally electropositive oxygen atom ends up in the oxycyclopropane ring and in the COOH group becomes COH, as shown in the reaction below. Epoxides may also be synthesized by the treatment of a halohydrin with a base. This causes an intramolecular Williamson ethers synthesis. The Williamson's ether synthesis is an SN2 reaction in which an alkoxide ion is a nucleophile that displaces a halide ion from an alkyl halide to give an ether. Intramolecular Williamson's ether synthesis occurs at a rate that depends on the number of atoms in the transition state.
As you can see in the picture, you can clearly see the proton transfer, which establishes an equilibrium, which then results as a intramolecular SN2, which is the definition of the intramolecular Williamson's ether synthesis. Here is an example of epoxide formation from halohydrins. First is proton transfer. As you can see, hydroxide deprotonates the halohydrin, establishing an equilibrium with the alkyl oxide ion. Second is the intramolecular SN2. The alkyl oxide ion functions as a nucleophile in an intramolecular SN2 reaction, ejecting the halide as a leaving group, leaving you with the product. Here we will be looking at reactions of epoxides with strong nucleophiles. When an epoxide is subjected to attack by a strong nucleophile, a ring opening reaction occurs. For example, consider the opening of ethylene oxide by a hydroxide ion. This transformation involves two mechanistic steps. Here you can see an example of an epoxide ring opening with a strong nucleophile. The first step is a nucleophilic attack. In the first step, hydroxide functions as a nucleophile and opens the ring in an SN2 process. The second mechanism is a proton transfer. The resulting alkoxide ion is then protonated by water, resulting in our product.